Do you know how to set up various kinds of DC analysis in SPICE? Do you know how to set up various AC analysis in SPICE? Do you know how to set up the variants of transient analysis in SPICE? Do you know why all the above three types of analysis are very important in VLSI? Stay tuned till the end of the video to know all the answers. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the significance of .op in SPICE simulation. Next, we will talk about the significance of .dc in SPICE simulation. Going further, we will talk about the syntax and example of .dc. Next, we will talk about the significance of AC analysis in SPICE simulation. Going further, we will talk about the syntax and example of the AC analysis, that is the .ac statement. Next, we will talk about the significance of the transient analysis, which is short formed as TRAN. Going further, we will talk about the syntax and examples of .TRAN. Finally, we will summarize our today's discussion. So that's the menu for today. Without any further delay, let's begin. Before beginning anything, I would like to mention that this episode and the next episode, we will be talking about the common genre of topics that are called the simulation control. That means how we control the different kind of simulation through different set of analysis. So let's move on to the next starting slide. .op significance. Here we will talk about the significance of the .op. So here goes our .op and it is written as .op only. It calculates the operating point of MOSFETs. Generally, we have a CMOS structure and we know that MOSFETs have some operating points and those are calculated by .op. The inclusion of this line in an input SPICE file directs the SPICE simulator to determine the DC operating point, also known as the Q point or quiescent point of the circuit with inductor shorted and capacitor opened. That means it's purely in a DC format. So all the nodes and the corresponding DC points are analyzed through this one single command. It's a very much kind of short instruction, but it operates on the entire circuit. That means the entire circuit, the whole set of nodes. And inductor shorted and capacitor opened means this is in a DC. Several steps are executed to get exact operating point and are documented in the simulation log. That means whenever you have a terminal, right, the terminal will give you the chronological output of the SPICE simulation. There you will have, also there will be a log file generated that will also have. So all the operating points will be given. Nowadays modern simulator has an option either to display all these things or suppress those things. So you must check also the modern simulators that whether this dumping option is opened or the dumping option is closed. This dumping option may vary from one simulator to another simulator, and here we are not talking about them, just touch basing the concept. It reports, that means the .op reports the following things. First, the node voltages, as I have mentioned, there will be a huge number of nodes in the circuit and the source currents. So there will be detailed calculation and the initial guess, that is the Q point, that means this Q point are calculated for all the node voltage and the source currents. Next, power dissipation at the operating point. So we have an operating point, right? It's a DC point and we calculate the power dissipation happening everywhere in the circuit, in all the nodes. Semiconductor device currents, conductance, capacitance, that means all the circuit element factors that are going to take part in the upcoming analysis, which might be a DC, which might be a AC, or which might be a transient or any other kind of analysis. So those are pre-calculated using the .op statement. The reporting may vary from simulator to simulator. This is, I also mentioned few lines back that the log may have well documented details of these operating points, or it may have that those are suppressed. So that depends from one simulator to another simulator. You should check the options to suppress or explicitly print all those options. Or even we are printing, there could be a shorthand print or it may be a explicit print. So that vary from one simulator to another simulator to shrink the size of the log file to save the disk space. So you must also take care of these options when you are using a proprietary simulator in the VLSI. We are done here with this particular slide by depicting all the significance that is associated with the .op, that is this much small command in this particular slide. Let's move on to the next slide. Here in this slide, we will talk about the significance of the .dc statement. The operating point or Q point, the quiescent point analysis is very crucial before performing full DC or AC analysis. That means we are calculating an operating region where the initial voltages of every node of the circuit or device under test, that is, it could be a MOSFET or it could be a CMOS, whether all those things are at the correct voltages points. So the operating point analysis, that's why it is very crucial. In DC analysis, capacitors and inductors are considered to be open and short respectively, as also we have talked in last slide that inductors will be considered open to DC because inductance is associated with AC only and capacitance is also associated with AC only. If it is DC, the capacitor will be open and the inductors will be short. So that is the assumption that we take when we do the DC analysis. .IC and .NOT set are very important at this stage. So have talked about the .IC and .NOT set already in the previous episodes. If you have not seen, I request you to see because these are explained in detail. DC analysis and operating point analysis statements are .DC, this sweeps for power supply, temperature, parameter, transfer curves, so all these things. And the .OP is for operating points to be calculated at specific time. So that means the DC is for sweeping the DC, but before anything we do, we must get the quiescent point or the Q point or the operating point through the .OP. That is the philosophy before beginning any simulation in the SPICE. So that must be there before we begin any kind of analysis. We are done here talking about the significance of the .DC through this slide. Let's move on to the next slide. Here in this particular slide, we will be going in detail of the syntax and example of .DC. So here is the syntax .DC, then we have the source name, then we have start value of the voltage, stop value of the voltage and incremental value of the voltage. And in case we have some other source, that can be also there. So source 2, start, stop and incremental value. Start means it will start at some value, stop means it will stop at that value, increment means there will be steps by which the voltage will get incremented. The .DC line defines the DC transfer characteristics curve of source and sweep limits. The source name is an independent voltage or current source of a resistor or the circuit temperature. Here could be a temperature also. In using the DC, we can also sweep the temperature of the circuit. V start, V stop and V INCR are the starting, final and incrementing values. So these three are explained here. Let us see some examples of the .DC. Here is the first one, DC, then V in is the source name, then 0.25, 0.5 and 0.25. This way we say that V in sweeps from 0.25 volt to 5 volt at the step of 0.25 volt. So you can correlate, this is start, this is stop and this is increment. This way you can correlate. Here example is DC, VDS, then 0, then 10, then 0.5. Then we have source 2 that is VGS, then 0, 5 and 1. So how we interpret it? We interpret this syntax as this sweeps VDS from 0 to 10 volt, that means from here to here with the step of 0.5, that means this is the step, and VGS sweep is from 0 to 5 volt at the step of 1 volt. That means for each of these sweep, right, there will be multiple VGS sweep. That's how it happens. Next, we have another example which is for the temperature. Now we write DC, then we write temp, and then we have the -55 to 125 and the step is 10. So how we interpret this? We interpret that the temperature is swept from -55 degree centigrade to 125 degree centigrade at the step of 10 degree centigrade. So in the first two example, we have seen single DC sweep, multiple DC sweep, and in the third we see the temperature sweep. Next, we have another example. It has much more bigger thing. So here the DC is there, the source is VCE and it starts from 0 goes to 10 at the step of 0.25. So how we interpret? Here the VC is swept from 0 to 10 volt at the step of 0.25. Now here again we have another source. This is a current source and it starts with 0 goes to 10 at the step of 1 micro. So how we interpret? Sweep the value of IB starting from 0 to 10 micro at the step of 1 micro. And you know the unit of current is ampere, so we add an ampere, that means microampere. So you have learned how to do the current sweep along with a voltage sweep here in this particular statement. Finally, we have another kind of DC sweep, that is the DC. Then we have RL load. It is a resistance. We have 1K, 2K as the starting and finishing line, and we have steps as 100. So how we interpret? Resistance sweep is done from 1K to 2K at the step of 100 ohm per step. So here you can see multiple kinds of example of the DC syntax. You can see the single DC voltage sweep, multiple DC voltage sweep. You can see the temperature sweep, the resistance sweep, and the voltage and current sweep. So you have seen 5 different kinds of example that you can do the permutation and combination. This way you can apply the syntax as per your requirement. We are done talking about the syntax and thorough example. Let's move on to the next slide. Here in this slide, we will talk about the AC analysis. Mainly we focus on the significance. After doing the OP analysis, which we have talked in the first slide, right? Pi simulator can conduct AC analysis of the nonlinear device such as MOSFET at the DC operating point. So once the Q point is done, then we can go ahead for the AC analysis. The .AC statement can do the sweep of multiple things containing frequency, element value, temperature, model parameter value, random sweeps such as Monte Carlo, optimization, and AC design analysis. So all this sort of thing are taken care by the .AC statement. Don't worry, we'll have examples for multiple things. There you will be understanding this significance. If this line is included in the input file, the simulator performs the AC analysis of the circuit over the specified frequency range. So we will do the frequency variation, right? And then variation, we can do the AC analysis of the circuit. Note that in order for this analysis to be meaningful, at least one independent source must have been specified with an AC value. So we need one particular independent source which has AC value. Typically, it does not much sense to specify more than one AC source. Obviously, in AC, either we will vary the voltage or the frequency, right? So there it doesn't make sense to have multiple AC in the same circuit. Generally, there will be a DC and a superimposed AC. If you do, the result will be superposition of all sources and difficult to interpret. So that means if we take more than one AC source in the circuit and try to analyze, the final outcome will have the cumulative effect of all the AC sources, and that will be very difficult to interpret, analyze, or debug. So that is the significance of the AC, and the things that we can get from the AC analysis are discussed here. Let's move on to the next slide to see some examples. Here in this slide, we will go through the syntax of the .AC and some examples to understand the usage. This is generally a sine wave format, just for your understanding that how the AC you expect, right? This is the most common waveform of the AC. However, AC could be something which has a periodic manner, not limited to the sine wave only. So here goes our syntax. Here we have the first syntax, the AC, then we have the dec, that is decade, then ND, then F start, then F stop, then we have another kind of sweep attached to it. The variable, then start, stop, and increment values. We have 3 forms. The second form is the change here is the OCT, that is the oct. And we have the linear. We have 3 different forms. And the different things in this 3 syntaxes means decade means decade-wise variation in the log scale. ND is the number of points per decade. Here you can see number of points per decade. Then we have oct is octave-wise variation. And NO is the number of points per octave. Lin is the linear variation. NP is the number of points. So here NP. We have F start is the starting frequency. F stop is the final frequency. So here is the F stop. So these are the things that you must know about the AC syntax. And here is the first part we have talked about. We will see examples for the sweep part also going further. So without any further delay, let's start the examples. First, we have a AC, then we have a decade-wise variation. Here we have 10 number of points per decade. Starting frequency is 1 and ending frequency is 10k. Next, we have AC and we have decade. Number of points will be 10. Starting frequency 1k and ending frequency 100 meg. Obviously, we are considering the default units of the frequency. Now we have the AC, then linear, then there will be 100 points. Starting is 1 and ending is 100 Hz for the frequency. Finally, we have the example containing the sweep. So first part is AC, then decade, then 10 points per decade. Starting is 1, final frequency is 10k. Then we have a sweep of C load with linear. Here the starting is 20. It will stop at 1 PF and the steps will be. So it seems that there is some typo here. Okay. However, you can understand that how the things will go on for the sweep. So you are done with the all flavors of examples of the .ac. So let's move on to the next slide. Here in this slide, we will talking about the significance of the transient analysis. Here are some transient waveforms that you can correlate with your general knowledge: sine, square, triangle, and sawtooth. This TRAN compute circuit solution as a function over time, that means the time range. Use of UIC. UIC is a command that is use initial conditions used along with the transient to calculate the Q points for the transient. We ensure to solve the quiescent points, that is the Q point, before beginning the transient analysis. That means this Q point analysis is coupled with the transient analysis and it is different from the default Q point analysis. Transient temperature sweep can be also taken care by this TRAN. Transient Monte Carlo analysis, that is the random sweep, also can be taken care by transient analysis. We can do the transient parameter sweep also. We can do the transient optimization through the TRAN command. Taking OP results as the initial value for the transient analysis. That means the transient analysis can run also with the .op, which calculates the initial Q points or quiescent points and start the transient analysis based off it. Also, alternatively, we can use the UIC or OP. So either you use the .op or you use the UIC, either one of them. So here goes the philosophy of the transient analysis by using the .TRAN statement. Now let us move on to the next slide. Here in this slide, we will talk about the syntax and example of transient analysis. .TRAN, T-step, T-stop, T-start, T-max and UIC. So this gives the transient syntax. T-step is the printing or plotting increment for line printer output. That means it gives the step by which the simulation jumps from one point to another point. T-stop is the finishing line for the time-wise simulation. T-start is the beginning line or the starting line, that is the initial time. If T-start is omitted, it is assumed to be 0. That means the starting line starts from 0. If we do not give the T-start, if it is not stated, means we are missing it. That means the time will begin from 0 value. The transient analysis always begins at the time 0 if this T-start is omitted. Otherwise, if the interval, that is 0 to T-start, the circuit is analyzed to reach a steady value, but no outputs are stored. That means once we specify time 0 to time T-start, calculation will happen. However, the data will not be stored for either for the waveform database or for the log or the text output. Nothing will be stored. All will be calculated and data will be stored from T-start. The interval, that is T-start and T-stop, the circuit is analyzed and the output are well stored for analysis. That means you do a text analysis or the waveform analysis, all the data will be stored. Tmax is the maximum step size default equal to T-step or T-stop minus T-start by 50. So Tmax gives the maximum step size. So the step size should not go beyond this value. Otherwise, this will be taken as the maximum step size. So T-stop minus T-start by 50, whichever is smaller. Tmax is useful when one wishes to guarantee a computational interval that is smaller than the printer statement. That means T-step. Here we are done talking about the syntax of the .TRAN and the philosophy of various factors associated with it. Let's move on to the next slide. .TRAN examples. So here is a sawtooth and here is a square, just again for your visual experience. Now let us start the examples. We have .tran, then we have 1 nanosecond, then we have 100 nanosecond. What does this signify? This signifies the transient analysis is made and printed for every 1 nanosecond for 100 nanosecond. Here we have omitted the start time. So the start time will be from 0 and the step is here 1 nanosecond. Then we have the TRAN, then we have 1 nanosecond, then 1000 nanosecond, and we have 500 nanosecond. Here we have specified the step. Then again we have TRAN, then 10 nanosecond and 1 microsecond. Again, here we are omitting the step. Next is .tran, 10 nanosecond, 1 microsecond. We have these two intervals. We have these two values. First one is the step and second one is the finishing line. And with this, we use a sweep for C load. Point of interest is 3 and 3 point of interest are given here. 1 picofarad, 5 picofarad, 10 picofarad. So let us see these by words, what I have just mentioned, right? So this means the calculation is made every 10 nanosecond for 1 microsecond at 3 C load values. PY is the point of interest and 3 values are given here. So here we have seen the transient analysis various examples to understand the philosophy that we have discussed in the previous slide. We are done discussing about the TRAN, that is the transient examples. Let's move on to the next slide. Summary. Let us summarize whatever we have discussed throughout our entire discussion. So we have discussed the simulation controls using the .op and .bc analysis, the .ac analysis and .tran analysis. So all these sort of analysis we have discussed in today's episode. We are done here. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in comments in the comment section down below, and bye for today.